Hello everyone watching this video. A warm welcome to the web series on thermodynamics on my YouTube channel. I am Sanjay Geji, an assistant professor at Mechanical Engineering Department working at Padma Bhushan Vasantrao Dada Patil Institute of Technology, briefly known as PVPIT, Budgaon, Sangli, affiliated to Dr. Babasaheb Ambedkar Technological University, D-Batu, Raigad. So this is the second video in this web series. In the first video I was talking about introductory things on the thermodynamics. So I discussed a lot of historical events which occurred during the development of thermodynamics. Then I talked about the invention of a steam engine, which was a turning point and a major cause behind the industrial revolution process. And this industrial revolution process actually brought about various changes to our life, and it impacted our lifestyle in a different way. It entirely changed the world order. Okay. Then there was the entry of electricity in the 19th century, which again gave a entirely new dimension and new meaning to human life, and it impacted our lifestyle in very big way. Okay. Then there was industrial development through various generations or various stages, such as Industry 1, Industry 2, Industry 3, Industry 4, through over the last 300 years. Okay, and in this year 2020, we are just moving through the process of or a shift of Industry 4.0. Nowadays, there is a lot of talk and lot of buzz about these crazy words like IoT, Internet of Things, AI, artificial intelligence, machine learning, data science, etc., etc. So the Industry 4 will be characterized by these new and upcoming and very exciting and super advanced technologies. Okay, but all these have some relation or some connection deeply rooted to the development of thermodynamics, and particularly an invention of a steam engine. So this is how we have to see its connection through this topic or through this subject. Okay, and we also saw various thermodynamic applications which are just around us and which are directly or indirectly relating to our human life. So all these things sum up and come up together, making this thermodynamics as a completely interesting package and a very interesting topic to learn. Okay, now note that all these videos are being made and published on my YouTube channel for the students of second year mechanical engineering who are right now studying, and particularly those students who cannot attend the live online classes on regular basis and miss out a lot of part. Okay, the reason may be anything like poor internet connectivity or unavailability of devices, some problem, some other personal problem, anything like that. Okay. Then so such students can cover up and make up all those lost part or missed out part by watching these videos on my YouTube platform. So that's why my attempt is to make these videos as simple as possible and as clear in a language as possible. Okay, so they can review these lectures and cover up all the parts the missed out. Okay, again, those students who regularly attend the live online classes but still have difficulty in understanding some important concepts right at that moment or that point in a live class. Okay, and they cannot even interact with the teachers due to lack of time. There are some other reasons to that. Okay, and I can understand that for such students who are regularly attending but still not able to keep up with the speed of teaching, because it is quite impossible or not possible to collect or gather all the things which are delivered during that lecture. So such students can revisit all those videos, all those parts from these web series videos on my YouTube channel, and they can access it on my on the YouTube, as it is freely and almost freely available and accessible from anywhere. So they can watch it anywhere at any time, and many times they can repeat these videos again and again till the point they can understand it completely. Okay, so that allows them this chance and this opportunity and time to understand the things in a well manner. Okay, so also there are some slow learners who can learn the subject at their own pace and at their as per their own convenience. Okay, and in the end all the students will be at same level. Okay, so there will not be much difference between who attended the live classes and speeded up their progress, and who later on viewed these videos through this YouTube channel, and then later on they can catch up. Okay, then there are some students of third year and last year mechanical engineering, or who have just passed out the mechanical engineering and are preparing for exams like GATE, competitive exams like Indian Engineering Services, Maharashtra Engineering Services, or who are just trying and preparing for technical job interviews or technical aptitude tests. All those students can review and revise and learn these concepts with a clear understanding. Okay, then there are some even the practicing engineers who are actually working. They can come here, they can watch these videos and revise and relearn whatever the parts which have been missed out during their learning period or studying period. So it will be like a brush up and touch up thing, and they can get something new out of it, and it will give them something new approach, and they can clear their concepts. It will bring the clarity and ideas, and they can easily apply them into their practice, and so that they can enhance their experience further. Okay, so this way the purpose and motive behind making these videos is quite clear and very broad in sense. Okay, so let's come back to the content of today's video, that is fundamental concepts of thermodynamics. Okay, I am starting off the content of thermodynamics. Before leading up to, I would like to recommend some books and references as a study material. Okay, so there are two interesting textbooks, that is Engineering Thermodynamics by P.K. Nag, which is Tata McGraw-Hill publication of third edition. See, this is the old edition. Now in 2020 they might have upgraded to like say 7th or 8th edition, but still you can manage with the old edition. If you have a latest edition, that will be much better. Okay, the same way another book, that is he is a foreign author, Yunus Sengel and Bowles, Thermodynamics and Engineering Approach. This is also Tata McGraw-Hill publication. These textbooks are quite sufficient to cover up maximum of syllabus, and this will give you, this is good for the early learners or first time learners. Okay, and there are some reference books which are very good in manner, and these can be referred when you are interested to go further deep, and you have developed some understanding of basic concepts, and you want to strengthen and boost your knowledge and information, and many other things are given at some depth. Okay, so you can go at length as per your special interest as you develop over the time. Okay, so these reference books like Van Weylen Sontag on fundamental of thermodynamics, this is the publication name, John Williamson's. The same way Moran and Shapiro, fundamentals of thermodynamics, are there. Okay, there are, apart from these books, there are some other reference books which are really good in nature, but just I have listed which are applicable and easily understandable for majority of the students. Okay, so that's about the references and study material. So this is going to be the outline of today's session. In that we are going to discuss some important terminologies and basic concepts of thermodynamics and some basic definitions. Thermodynamic system, thermodynamic surrounding, thermodynamic universe, various types of thermodynamic systems and their practical examples of these systems, and lastly system boundary. Okay, all these terminologies and definitions I will explain with the help of practical applications. I want to make these videos or these sessions completely practical oriented, because I don't want to limit the things to just listing up the theories and definitions. Okay, so that's okay, but you should have a good understanding to how to use these terms in practice and in real life or in real time scenarios. Okay, that skill you have to develop to be a better engineer or to be a quality engineer. Okay, so my all attempt throughout all this web series will be to be a practical oriented, to support all the theories with practical examples and practical situations, so that that will give a clear link between theory and practice. That will you will be able to fill up the gap between theory and practice. Okay, so let's move on. So these are the concepts we have to see. So first one is a thermodynamic system. It is defined as a part of a space or a region or quantity of matter on which our study will be focused, or the thing in which we are interested to carry out some analysis, some design, some anything. Okay, by applying various principles and laws of thermodynamics. Okay, then surrounding, everything which is outside and external to the system is called as surroundings or environment. Okay, this next is boundary. A boundary is an imaginary or a real wall which divides or separates the system from its surroundings. So this boundary may be fixed or may be moving. Okay, then next is the thermodynamic universe. A system and surrounding together comprise a thermodynamic universe. So system plus surrounding equal to universe. It's a simple equation. Okay, now have a look at this figure. In this way a general idea of system, surrounding and boundary is explained. So system can be any part of any shape in a space or a region, or it may be a matter, okay, which is taken for the study. Okay, and its outer boundary, outer covering or outer surface will be forming a boundary, and everything which is outside or external to this system is a part of surrounding. Okay, everything which is not coming into system will be treated as a surrounding. Okay, another picture you look at. So this is system, this is a clear system boundary, and everything outside it is a surrounding. So system plus surrounding will make entire universe. Okay, this is the conceptual diagram. So next is how the interaction between system and surrounding can take place. Okay, what happens between system and surrounding? It is known as an interaction. So two types of interactions are possible. One is the mass interaction and the second one is energy interaction. Okay, so the system will be having a certain mass. So this mass may be increasing, may be decreasing, depending upon how much mass is coming into the system and how much mass is going out of the system. So mass transfer is possible into and out of the system. Okay, so this is known as a mass interaction. In the same way, system will be carrying some energy content. Okay, so it will increase or decrease depending upon inflow of energy and outflow of energy. How much energy is coming from the surrounding to system and how much it is exiting from system to surrounding. Okay, so these are the interactions by which by which the various processes can be assessed and evaluated. Okay, then to understand how this system, surrounding and universe, the concepts, how these work in practice, let us look at this simple example of a pressure cooker. Okay, this pressure cooker, as we know, we are well aware, it is a device used in kitchen for cooking the foods like rice or vegetables by steaming process. Okay, what you do is some vegetables or rice is put into this container and some water is added to it. It is put, then it is put on a gas with a closed lid on it. Okay, so by absorbing the heat, water converts to steam at certain pressure, and the steaming process, cooking takes place by steaming. Okay, and this steam, whatever steam is generated inside at certain pressure, will not be allowed to escape to outside, because of tight sealing of this top cover. Okay, and this small thing at the top, as you see, this is actually a dead weight pressure release valve. Okay, this is particularly provided to maintain and ensure the safety of working of the pressure cooker, because if no opening is provided, what will happen? Due to overheating, the steam will produce, and pressure inside will build up. It will increase beyond the safety level or safety margin. So in that case, it will lead to explosion or some accident. So to avoid that, this dead weight pressure valve is designed in such a way that whenever there is a pressure rise inside the cooker, it will lift up this weight of the wall and thereby opening the passage, and excess amount of steam will be released to outside, to surrounding. Okay, and when this pressure inside the cooker falls back to normal level, or within operating zone, within a safe level, on account of its weight, it will come down and it will close off the passage. Okay, so it will be again a closed thing. Okay, this is how the pressure cooker works. Now suppose we are interested to we are interested to know how much heat energy is required to cook a certain amount of rice. Let us say to cook 1 kg of rice, how much amount of heat energy is required and how much time it takes to cook it. Okay, so for that, to handle this case, first we have to clearly define what is a system. Okay, sorry for the little mess up with the presentation. I wanted to take a pen. Just let me allow me take me pen. Okay, so we have to first, where is the, just a moment, sorry again for a little shake up. So I was talking about, first we have to identify what is a system and what is a system boundary and what is the surrounding. Okay, so look at this photo now. A pressure cooker is put on a gas, okay, for a cooking. Then so we will first clearly identify or define what is a system. So this cooker, this will be a system, okay, containing this rice and water inside it. Okay, this cooker body is a system. This external surface of this cooker body is forming a system boundary like this, including the handles, including this bob. Okay, so this is how you have to set up the system boundary. Okay, so this is the system boundary, and everything which is outside to it, as seen in this photo or this figure, everything or the other objects like this, gas or stove, burner, everything, this is all these are part of surrounding. Okay, this is surrounding. Okay, so having identified what is the system and what is the surrounding and where is the system boundary, this is system boundary. Okay, so let us look at the interactions, how it is how process of interaction between system and surrounding are happening. Okay, now this pressure cooker is put on a gas, so there is a burning flame. So this stove being a part of surrounding, the heat is being transferred from system to surrounding. Let me take another pen. So there is a heat transfer from the burning flame of a gas from and direction is from surrounding to system. Okay, so this is the energy transfer, and heat is crossing the boundary here. Okay, so this is the energy transfer, and when there is a pressure rise and some steam is released from this bob, there will be a mass transfer. Some amount of steam is coming out from system to surrounding, okay. So this is energy transfer, this is a mass transfer. So this way we have to identify what are the how many interactions are there for mass transfer and for energy transfer, and in what way they are taking place. Okay, but after identifying all these things, we can apply the principles and laws of thermodynamics and perform and complete our calculation or analysis part, such as finding out how much energy is consumed and how much heat energy is consumed, and how much time has been how much time required for the cooking. Okay, so this was a simple example. In this way, in practice, you have to do this exercise many times for much bigger and complex systems, such as a thermal power station, nuclear power station, or a rocket engine, etc., etc. Okay, in that case, even though these are very simple terms simple terms to learn, but still you should have a clear understanding of it, because when it comes to a bigger systems like rocket engine, there are many components which form the subsystems of that bigger system. Okay, so that makes a very critical thing to decide whether what is a system and where is the system boundary, and how they are, what is forming the surrounding, and how they are interacting with each other. Okay, to perform a complete system analysis, this thing is very, very important. Okay, so let's move on next. Then there are these 4 types of thermodynamic systems. First one is a closed system, or also known as control mass. Second one, adiabatic system or insulated system. Third, open system, or also known as a control volume. And last one is a special case of isolated system. Okay, then first one is a closed system or a control mass. Now look at this look at this figure. It is a closed system is a system of a fixed mass. It means that mass cannot cross the system boundary. Okay, but energy in the form of heat or work can cross the system boundary. So this is some system having no inlets or no outlets. So mass transfer is not allowed. Mass transfer is not possible. So mass of the whatever mass is there within the system will remain constant throughout the process, and system will interact with the surroundings only in the form of energy. So energy in the form of heat may come into the system or may exit out of the system. So in short, mass transfer not possible, but energy transfer possible. Okay, this is the simple idea of closed system. Okay, just for example, consider this figure. A piston and cylinder arrangement. This is a piston, which is a moving part which can move in up and down direction. A device containing a fixed mass. Now suppose this is containing some gas of mass m with no inlet outlet. There is no inlet or outlet to transfer this mass. Okay, so mass transfer is not possible, and but energy transfer across this system boundary is possible. Okay, so this across this container is possible. So this is a simple example. Let us look at some practical examples. Take this LPG gas cylinder, which is a common utility at our homes and kitchens. Okay, LPG gas is present in it at some pressure, and there is a regulator at the top which regulates the flow of gas to the burner through this gas tube whenever the knob of stove is opened. Okay, so as long as the gas burner is not in operation or knob is closed, this regulator will be in closed position, and it will maintain the gas inside at high pressure. And it will not allow the leakage of this gas inside. So mass of mass of the gas inside the LPG cylinder will remain constant. Okay, in the same way, tire and tube of a wheel of any car or any vehicle, it is filled with some gas like air or nitrogen at some pressure, thereby it remains inflated. Okay, and there is a non-return valve or a charging valve. Okay, so as long as this valve is closed, it maintains its shape and it remains inflated. So this is an example of a closed system. But when you release this air through this, okay, there will be a mass transfer from it, from inside to outside. Okay, so in this way you can find many examples of such closed system surrounding you. Okay, then next is a adiabatic or insulated system. A system which is thermally insulated, that is heat transfer is not possible across the system boundary, is called as adiabatic system. Okay, example is a thermos flask. Okay, a thermos flask is a device which is used to store the hot or cold drinks inside it and maintain its hotness or coldness over a longer duration of time. Okay, so this construction is like this. There is an inner flask and there is an outer flask, and a vacuum insulation is provided in between. So there is in between this gap there is a vacuum, complete vacuum. Okay, and insulating materials are provided. Insulating materials are those one which retard the heat transfer or which prevent the heat transfer across them. Okay, so suppose a hot water or hot tea is placed in it, so heat transfer from hot water or hot thing to the surrounding cooler environment will not happen quickly, and it will stay it will stay hot for some 3 to 4 hours. Okay, in this way the adiabatic system works. Since this cover is completely closed, its opening is closed, it will be like a closed system. So simply whenever there is a insulation provided for a system, it will work as a adiabatic system. Okay, so no mass transfer possible, no heat transfer possible. Okay, these are the two conditions for a insulated or adiabatic system. Okay, just another example, a tank containing some gas like a helium at a certain pressure. It is a closed tank having insulation surrounding it. Okay, so no heat transfer is possible. Now this is a special case where mass transfer will not be possible due to closed system. No mass transfer possible, no heat transfer possible due to insulation provided surrounding it. But mechanical work transfer is possible. Suppose we are having a stirrer like arrangement here, where the shaft is crossing the wall of the cylinder or wall of the tank, and it is entering into the system. So this is the way of mechanical work transfer from surrounding to system. Okay, so this is possible in case of adiabatic system. Okay, so then next is a more general case, that is open system or control volume. In this, both mass transfer and energy transfer are possible. Okay, so open system or control volume is a properly selected region in a space. Okay, some space or some part of a system is selected or taken as an open system having some inlet and some outlet. Okay, so mass transfer across the system boundary is possible. Energy transfer is also possible in various ways, maybe heat transfer, maybe work transfer. Okay, example, let us see. Many of the engineering problems involve mass flow in and mass flow out of the system, and therefore these are modeled as the control volumes. Examples are fluid flow through nozzle, a pipe, flow through pump, compressor, water heater, turbine, etc. So many such devices which are known to be a steady flow devices have some mass flow in and mass flow out. At the same time, they have energy flow in and energy flow out. Okay, so with this figure you can easily understand mass can come in, mass can go out through inlet and outlet, and energy can cross the system boundary via heat or via mechanical work or some other mechanism. Okay. Very interesting example of a solar water heater working as an open system. So see, this is the solar water heater body. Okay, that we know how it works, that solar heat energy is used to heat up the water, cold water, and thereby hot water generation takes place by absorption of heat, and that hot water is then supplied to the point of use in bathroom or kitchens or wash basins, etc., etc. Okay, and such hot water heaters, solar rooftop heaters, have been a common utility nowadays at various residences or commercial buildings or at the top of hospitals. Okay, so now consider here this outer surface of this entire solar water heater is forming a system boundary, and this hot water storage tank and these tubes are the components of a system, and everything outside here is surrounding. Everything outside there is a part of surrounding. Let me draw this for you so that you can easily understand. So this is how we can set up a system. So this line, this red line, is actually a boundary, and everything outside will be a part of surrounding. Okay, so consider the processes. So water comes in, cold water comes into this solar water heaters, and hot water leaves out. So water, in terms of water flow, mass transfer is possible. Okay, in the same way, solar radiations are falling onto these tubes, and these radiations are carrying some heat energy, and this heat energy is absorbed by these black tubes, copper tubes, and that heat is then transferred to water, which is circulating throughout these tubes, and thereby water heating takes place. So solar heat energy is crossing here. Solar heat radiations are crossing the system boundary here. So that is the energy transfer. Okay. Another example, look at this. A domestic water pump is a common utility at our homes or residences, commercial complexes, to transfer or lift up the water from the underground tank to overhead tank, covering some height of the building. Okay, so here we can set up the system boundary like this. So this pump body will be a system. Okay, and this is how I can draw the system boundary around this pump. So this part, suction pipe which is entering into the pump, this will be inlet. Okay, this will be the inlet, and the discharge pipe which is exiting out of this system, this will be out. This will be outlet. Okay, so water is sucked in. So water inflow is there into the pump body. Okay, and the same amount of water is leaving out through this outlet or a delivery pipe. Okay, so water is coming in, water is going out. So mass transfer is possible across the system boundaries. Okay, and to drive this impeller of a pump, usually we use the electric motor, which supplies the mechanical shaft work by conversion of electricity into rotary mechanical shaft work, and that rotating shaft is coupled to the impeller, which is rotating here. Okay, so mechanical work or mechanical energy is then transferred to this impeller, and this impeller transfers that mechanical work or energy to the water by the centrifugal action, and thereby its pressure is increased. Okay, so work is transferred to water to increase its pressure head, that is, and thereby water reaches or can travel this much height. Okay, so this is how example of open system covering the including the mass flow and mechanical work transfer. So this was the example of a mechanical work transfer. Okay, and this was the example of heat transfer as a energy transfer. Okay, so this way you can identify as many examples as possible out of your day-to-day life experience. You just have to be aware, and you just have to be attentive, okay, and have some clear idea, so that you can manage it out, how to identify a system, how to set up a system boundary, and how to identify a surrounding. Okay, then a special case of an isolated system. In this system, neither mass interaction is possible nor energy interaction is possible in any way. So mass transfer, no mass transfer allowed, that is no mass coming into the system and no mass leaving out of the system. Here again, no energy coming into the system and no energy going out of the system, so completely isolated. Okay, now this isolation term has become quite famous in this COVID pandemic situation era. Okay, and since our lockdown also, we have been familiarized with the words like isolation, quarantine, etc., etc. So just to realize this system as such, consider a patient with a COVID-19 positive result, and he is suffering from that COVID-19 sickness infection. For first 14 days he is put into isolation ward or isolation room. So what it means, so that isolation room becomes an isolated system for him. Okay, so man will be isolated within the system from outside world or external external things. So only food and medicines are delivered to him. Okay, so it is not a completely isolation, it is a partial isolation. Okay, and for 14 days he is totally isolated from the outside world. Okay, the same was happening with lockdown also. During lockdown, there was a total ban on entry and exit of people from certain location, like Sangli city city and Sangli district was closed, totally locked down. So there was no any transfer of people or goods or items from the city to outside world, or from outside world to city. That was the case in lockdown. So that can also be taken as a isolated system. Okay, of course it cannot directly relate with the physical systems. Just I am taking that for example, because these systems are very rare to find in practice. That's why I had to quote in terms of a common experience. Okay, then again you can take a Thermos Flask as a isolated system. Okay, because we saw that in case of adiabatic system or insulated system, it is provided with a complete insulation or a vacuum insulation, thereby heat transfer is not possible across this wall, and mass and being completely closed at the top, mass will remain inside here. It will not transfer from inside to outside, or anything is entering from outside to inside. So keeping it constant, mass constant. Again, there is no any provision to transfer energy in some other form, like mechanical work. It is also not possible. So all these three things not possible, that make up the isolated system. No mass transfer, no heat transfer, no energy transfer. Okay, that's it. Next, a system boundary types. Okay, we have seen so many systems and identified by separated from its surrounding in terms of system boundary. So for boundary there may be three types. One is fixed boundary, the second one is moving boundary, and third one is imaginary boundary. Okay, now through these diagrams and examples you can understand. Now see, this is some part of a nozzle body taken for a study, so that is forming a system. So boundaries are set up like this. This is some inlet and this is some outlet. Okay, so at inlet and outlet, these are both open passages. Okay, there is nothing material available there. Okay, so that will be a imaginary boundary. So inlet and outlet are the imaginary boundaries. Okay, but in case of a nozzle body which is a rigid wall, so this is a real boundary. This is a, this dotted line, you can understand, a real body. Okay, and since this body is rigid, it will be a fixed real boundary. Here it is an example of fixed real boundary. Okay, same way here, cylinder and piston arrangement taken. Piston is moving, so piston can move. So this boundary, along with the piston's motion, boundary can move in up and down direction. So this becomes a moving boundary for a real boundary. Okay, and there is one inlet to this cylinder. So this part, this much portion will be, let me show you with this pen. This much portion, this portion will be imaginary boundary. Imaginary boundary. Okay. So that's it. With this, I am finishing today's session. Thank you for watching the video entirely, through giving your enough sufficient time. And if you haven't subscribed yet, please, it's a kind request to you to subscribe to my YouTube channel and hit the notification bell icon, so to receive latest updates about the videos and new things that I upload. Okay, then if you like the videos contents, and you can like it, and you can share it, and you can forward the link to your friends and colleagues, so that they can also become aware of this. Okay, then if you have any questions regarding this topic, or regarding anything of thermodynamics as such, or any technical terms, you can ask these questions in the comment box, or you can contact me on my WhatsApp number or email ID. You can even email me. Okay, and if you have any feedbacks about quality of video, audio, if you want to you want something, you want to add something, okay, you can put that through the comment box. You can put all your views in the comment section. All are welcome. Okay, so I hope you are all enjoying these videos, and getting some insights, and getting some practical approach to the subject. Okay, thank you very much all. Come again for the upcoming lectures, videos.